welcome to this series of lectures on the theory of time. What is the theory of time? It's kind of a counter theory to Einstein's theory of relativity. Over these next 4 lectures, we're going to cover different parts of this theory of time. In this first lecture, we're going to cover what we call the Romeo Effect. In the next 3 lectures, we'll talk about assumptions that we make for this theory of time and how they either agree or disagree with the assumptions that Einstein made in his theory of relativity. We probably are all familiar with the story of Romeo and Juliet from William Shakespeare. We probably had to read it back in high school literature course. It's a story of 2 warring families, the Capulets and the Montagues. And their children, Juliet and Romeo, are in love. And the 2 families do not want these 2 children to marry. Romeo and Juliet do marry in secret. But what do we remember from this story? Typically, it's the balcony scene. It's the scene where Romeo says, "But soft, what light through yonder window breaks? It is the east, and Juliet is the sun." And we also have Juliet saying, "Romeo, Romeo, wherefore art thou Romeo?" Now, what does this have to do with the Romeo effect? Absolutely nothing. My name is Victor Meyer, and I consider myself an amateur theoretical physicist. Now, I do have degrees in Masters of Arts in Mathematics and Computer Science. I was once also chairman of the Department of Mathematics and Computer Science at the University of St. Mary's in Leavenworth, Kansas. Why do I call myself an amateur theoretical physicist? Well, it's because I have not had a lot of formal physics training. My highest physics training was in a general physics course back as an undergraduate student. Is this good or is this bad? I think it's good. I think it's good from the standpoint that I was never indoctrinated into the current scientific belief that Einstein's theory is correct. Everything we see in the scientific community does not challenge Einstein. It tries to extend Einstein's theory into other areas. Having not been indoctrinated into physics, I'm able to think outside the box a little. And in thinking outside the box, I am questioning the assumptions that Einstein made in developing that theory. So, in this lecture, I said we're going to talk about the Romeo effect. What is the Romeo effect? Well, it's not the balcony scene. The Romeo effect comes much later, in scene 5 of Shakespeare's play. Let me set up the scene. Juliet's family, the Capulets, decide that Juliet should marry Paris, whom they find favorable. Juliet, even though she's been secretly married to Romeo, does not want this thing with Paris to happen. So she goes to an apothecary, she gets some drugs that causes her to faint death. Doesn't kill her, just makes her look dead. She writes a note to Romeo to let him know what she's planning. Unfortunately, Romeo never gets this letter. Instead, Balthazar, who is Romeo's best friend, hears that Juliet has died, that she has committed suicide. And this is what Balthazar reports back to Romeo, that Juliet is dead. Well, you can imagine this devastates Romeo. The love of his life is dead. So what does Romeo do? Romeo goes to an apothecary. He also gets some drugs, but these drugs are not to feint death, but rather they are to cause death. He takes the drugs and he goes to the crypt where Juliet is laying. There is a famous picture, it's being held in a private collection. It was painted in 1886 by an English artist named Francis Sidney Muschamp. And this picture portrays the moment that Romeo decides to commit suicide because he thinks his beloved Juliet is dead. I'm going to read two sections from scene 5. In the first section, we have Romeo's observations of Juliet laying in state. And Romeo says, "For here lies Juliet, O my love, my wife. Death that has sucked the honey of thy breath hath no power yet upon thy beauty. Thou art not conquered. Beauty's ensign yet is crimson in thy lips and in thy cheeks, and death's pale flag is not advanced there. O Juliet, why art thou yet so fair?" Romeo's looking at Juliet. Her cheeks, her lips are still crimson. Her body does not have that pale look that comes when someone dies. In fact, she pretty much looks the same way she looked when she was alive. But for some reason, Romeo doesn't dawn on him that Juliet is not dead. He believes what his best friend Balthazar has told him, that Juliet is dead. And so what happens next is from this next part of the play that I shall read here, where Romeo makes his decision as to what he's going to do. And it goes, "Here will I set up my everlasting rest, and shake the yoke of inauspicious stars from this world-weary flesh. Come, bitter conduct, come, unsavory guide, thou desperate pilot, now at once run on the dashing rocks, my seasick, weary bark. No more. Here's to my love. Eyes, look your last. Arms, take your last embrace. And lips, to you the doors of breath seal with a righteous kiss." And with these lines, Romeo takes the potion and commits suicide. What is the Romeo effect? The Romeo effect is making a bad decision based on a bad assumption. Juliet is not dead. So the fact that he thinks she's dead is a bad assumption. And because he believes in that bad assumption, Romeo makes a bad decision. And this is what I think is happening with Einstein's theory of relativity. When in today's scientific community, you don't challenge Einstein's assumptions. Einstein is treated pretty much like a god. You can build on his theory, but you don't challenge his theory. In the theory of time, we're going to challenge his theory. We're going to challenge the assumptions that Einstein made when he developed the theory of relativity. Are there other examples where scientists got it wrong, made a wrong decision based on wrong assumptions? Well, there's lots of examples. One that comes to mind is before 1969, astronomers were trying to theorize, how did we get the moon? How did the moon end up in orbit around the Earth? The leading theory was that somehow the moon was a planetoid traveling through our solar system and got caught up in Earth's gravity and went into orbit around the Earth. So it's a captured planet that's just wandering through the solar system. What happened in 1969? Well, we sent the Apollo 11 astronauts to the moon. They collected rocks. They brought those rocks back to Earth. Those rocks were tested. And what did they show? They showed that the moon was made of the exact same rocks as the Earth. In other words, the moon had come from the Earth. Okay, when astronomers were asked, well, how did you get this theory so wrong? They said, well, we didn't have much information to go on. We just made some bad assumptions. So let's look at, briefly, the whole idea of a theory. What is a theory? A theory generally starts off with a definition of something. Then it has some axioms. Axioms are assumptions. An assumption is something you do not prove or you can't prove. It's just something that you accept as true. After that, you prove theorems. These theorems are proved either by taking what was given to you or by applying one of the axioms, one of your assumptions, or by applying a previous theorem that you had already proven. We're going to give you an example from linear algebra. And this example talks about the definition of a field. And it goes like this. A field is a set K of elements. For each pair A, B of elements in K, there exist elements A plus B in K called the sum. What are we talking about here? We're trying to define a field. The elements are going to be numbers. They don't have to be whole numbers, but we'll simplify things. We'll use whole numbers. And what the definition says is that if you've got a set of these numbers, then you can add any two numbers in that set, add them together, and get another number in that set. That's all the definition. Okay? What are the axioms? Well, we're going to have 4 axioms. You probably remember these from high school algebra courses. The first axiom is the associative principle. It says that it doesn't matter the order in which you add things together. You can add A plus B and then add C, or you can add B plus C first and then add in A. That's the associative principle. Then there's the commutative principle. The commutative principle says it doesn't matter in which order you have the elements around this plus sign. A plus B equals B plus A. So 5 plus 7 is 12. 7 plus 5 is also 12. That's the commutative principle. The third axiom is the identity principle. The identity principle says that you have an identity element within the set such that when you add anything else to that identity, you end up with that anything else. So that identity element is 0. When you add it to, say, 5, 0 plus 5 gives you 5 again. 0 is the identity element. That's the identity principle. And finally, we have the inverse principle. The inverse principle says that for every element in the set, you also have its inverse element. What's the inverse element of 5? It's negative 5. Having both 5 and negative 5 in the set, when you add them together, you get 0, which is the identity element. So the inverse property says you got the inverse in the set, and together the inverse and the original number add together to give you the identity element. All right, so let's take a look at a couple of different sets to see if they satisfy this idea of a field. Let's first look at the counting numbers. 1, 2, 3, 4, 5, 6, 7, 8. Okay? When you add any of these numbers together, the results in the set, the associative property applies to them, the commutative law applies to them, but the identity principle does not. It does not apply because you do not have the identity element, 0, in the set. So let's add 0 to the set. Now we're going to have 0, 1, 2, 3, 4, 5, etc. We have the identity element, but we still do not have the inverse elements. We have 5 in the set, but we do not have negative 5. So integers starting with 0 is not a field. The only time we have a field is if we have a set that has all the positive integers, 0, and all the negative integers. So the whole set of integers, negative, 0, and positive, together form a field. So having talked about the definition and the axioms, let's look at a simple theorem. The theorem is this: if A plus C equals B plus C, then A equals B. Now notice here, there's logic involved. We have a construct of if, then. If this condition is true, then this conclusion follows directly and is true. The results must be logical. If the result is not logical, then either something is wrong with our proof, or our assumptions are not true, or we just don't have a field that we're working with. We're going to go prove this theorem. A plus C equals B plus C means that we have A equals B. All right, so what's our given? Our given is A plus C equals B plus C. Because of the inverse property, we know that the inverse element of C is in our set. Therefore, we can add negative C to both sides of the equation. That's because we have a field. Inverse elements are in the field. In the next line, we're going to apply the associative principle. We're going to move the parentheses. Instead of A plus C plus negative C, we're going to have C plus negative C and then add A. That's the associative principle. Next, we're going to apply the inverse principle. The inverse principle says that when you add a number and its inverse, the result is 0. So what we end up with is A plus 0 equals B plus 0. Finally, we apply the identity principle, which says when you add the identity element to any other element, you get that same element back. So A plus 0 equals A, b plus 0 equals b, we end up with a equals b. So our theorem is true. If we start off with a plus c equals b plus c, we can conclude that a equals b. All right, so let's take this out of pure math and take it into Einstein's theory of relativity. Einstein had two forms of his theory of relativity. He had the special theory of relativity, and he had the general theory of relativity. What's the difference? The general theory of relativity deals with gravity. The special theory kind of assumes gravity doesn't exist. In the special theory, objects in space just move around under their own inertia. What is inertia? Well, it goes back to Isaac Newton's laws of motion. Any object in motion stays in motion unless operated by some force. Well, that force would be gravity, but we don't have gravity in the special theory. So objects in outer space are just moving under their own inertia. Einstein is going to say that each of these objects in space is in their own inertial frame of reference. There's that word inertial again, inertia. So each star, planet, whatever, is moving in its own inertial frame of reference. And these are all independent from all the other stars that are out there in our universe. What assumptions does Einstein make in his special theory? Well, first, he assumes what's called the principle of relativity. The principle of relativity has been around for a long time, way back to Galileo. And it says that in space, there is no concept of something standing still. If we have a star moving 1,000 miles per hour, well, the question is 1,000 miles per hour relative to what? There's nothing standing still. We can only say it's moving 1,000 miles per hour relative to something that we're going to assume is standing still. Typically, that is us here on Earth. We assume that us as the observer is standing still. So some stars are moving 1,000 miles per hour. Another star may be moving 1,000,000 miles per hour relative to us on Earth. Now, a point about the principle of relativity is that any experiment that you perform on any one of these inertial frames of reference will yield the exact same result. For example, let us try to measure the speed of light in a couple of frames of reference. We've got this star that's moving 1,000 miles per hour. We're inside that frame of reference, so we send out a beam of light, bounce it off of a mirror, it comes back to us, we measure the distance and the time, and we get a velocity for the light. It turns out to be the constant c, what normally we think of as the speed of light. Einstein was very big on the constant c being a constant value for the speed of light. Well, let's look at the star that's going 1,000,000 miles per hour. And we're going to perform this same experiment inside its inertial frame of reference. So, even though the star is moving 1,000,000 miles per hour, we're inside that frame, moving at that 1,000,000 miles per hour. We send out a photon, bounce it off a mirror, it comes back, we detect it, we measure its distance, its time, and what do we get? We get the speed c. So it didn't matter if the star was moving 1,000 miles per hour or 1,000,000 miles per hour. When we performed the test within those individual frames of reference, we get the speed of light to be c. That's the idea of any experiment you perform in any inertial frame of reference will yield the same result. Now, as a result of that, you cannot tell in which frame of reference you exist. If you're in that frame of reference where the star is moving 1,000 miles per hour, you measured c for the speed of light. If you were in that frame of reference where the star was moving 1,000,000 miles per hour, you still got c for the speed of light. You cannot tell in which frame you exist. That is the principle of relativity. Einstein's next assumption was the principle of invariant light speed. Now, I mentioned earlier that Einstein was kind of fanatical about the speed of light being this constant c. He thought this was something which brought order to the universe, something that had a definite velocity upon which everything else could be measured. So he assumed that in the vacuum of empty space, light travels at the constant speed c. We can kind of see how he came up with that, because in every frame of reference we're in, we will always measure the speed of light to be c. So it seems like it might be logical that the speed of light is c in the vacuum of empty space. What we're not necessarily told when we are given this assumption is that Einstein is assuming that the photons are traveling independent of the light source. What do we mean by traveling independent? Consider that frame of reference where the star is moving 1,000 miles per hour. What Einstein is saying is that as soon as a photon leaves that star, it will immediately travel at speed c. Has nothing to do with the fact that the star is moving at 1,000 miles per hour. The speed of the photon will be c. In that frame of reference where the star is traveling 1,000,000 miles per hour, as soon as the photon leaves the star, it will travel at speed c, regardless of the fact that the star is traveling 1,000,000 miles per hour. Okay, so the speed of light is independent of the source. The source could be going 1,000 miles per hour, or it could be going 1,000,000 miles per hour. Doesn't matter. As soon as the photon is generated and is moving through empty space, it's going to move at exactly the speed c. That is this concept of the independent speed of light, independent of its source. And that is a part of Einstein's principle of invariant light speed. All right, Einstein made one more assumption. This assumption is in his general theory of relativity. Remember, general theory of relativity deals with gravity. And what Einstein said is that we live in a four-dimensional space-time. Space-time being one word. Now, space-time was not an invention of Einstein. Space-time came from a teacher of his named Hermann Minkowski. But Einstein used the concept of space-time to illustrate his general theory of relativity. So Einstein says that there is four-dimensional space. What do we mean by this? First, we mean that there are three spatial dimensions. We are all familiar with them. They are length, width, and height. What makes them spatial dimensions? We can measure. We can take anything and measure its length, its width, and its height. So a spatial dimension is something that can be measured. What about the fourth dimension? The fourth dimension is time. Time is not something that you can measure spatially. Things just move around in time. In fact, physicists will argue that the velocity of time is zero. It has no motion. It is just something that causes things to move. When Einstein says that we live in four-dimensional space-time, he is saying, and this gets confused sometimes, he's saying that we live in three spatial dimensions and one temporal dimension. Temporal meaning time. Well, what makes Einstein this genius that he is today? He takes his theory and he proves something or does a calculation that had not been possible before. What is that thing he does? Well, astronomers had a problem with something called the precession of the perihelion of the orbit of Mercury. That's a bunch of words. Let's break it down into its pieces. We all know that Mercury is a planet. It's the closest planet to the sun. We know that the planets orbit around the sun. Hopefully we also know that the orbit is not circular. It is elliptical. All right, so when it's elliptical, there is a point where the planet is closest to the sun. That is called the perihelion. There is another point on the other side of the ellipse, the aphelion, where the planet is the farthest from the sun. But we're going to look at that point where it's at its perihelion, its closest point to the sun. So we have the perihelion of the orbit of Mercury. The last piece to this is what we call the precession of the perihelion. As Mercury orbits the sun, this perihelion does not stay in the same place. Instead, it advances with each orbit. So as Mercury orbits around the sun, this point of perihelion is moving. That is called the precession of the perihelion of the orbit of Mercury. Prior to Einstein, the only theory around that astronomers could use to measure that precession was Isaac Newton's general gravitation theory. When they applied Isaac's general gravitation theory, they did not come up with an exact answer or a good enough answer to match the observational evidence that they were seeing on this precession of the perihelion. So they knew that Einstein's theory, or that Isaac Newton's theory, was somehow incomplete. It lacked something because it was not making an accurate calculation of something due to gravity. Einstein takes this problem on as a challenge, and he applies his general theory of relativity to the problem. And remember, what's the difference here now between Newton's theory and Einstein's theory is this idea of time being a fourth dimension in space-time. Isaac Newton only thought in terms of three-dimensional space, length, width, and height. Einstein is adding in time. And when he does this calculation, adding in time, he comes up with a pretty exact answer to this problem of the precession of the perihelion of Mercury. This result says that Einstein's theory is better than Isaac Newton's. And so people are hailing Einstein as almost a god at this point because he has come up with a theory which gives us better calculations on the laws of gravity. Okay, so what's bad about Einstein's theory? I mean, we're developing this theory of time for some reason. So let's talk about where Einstein is coming up with stuff that seems to be maybe a little illogical. Well, if you take the principle of relativity and the principle of invariant light speed, these were his two assumptions in his special theory of relativity. If those two assumptions are true, then you have time dilation. We'll go through that proof in a later lecture, but right now it's, if these two assumptions are true, you must have time dilation. Well, what is time dilation? Einstein argued that time dilation was like what he called the traveling twins paradox. The idea is that you've got two twins, born at the same time, same age. One twin decides he's going to go off into space, and he goes at high speeds around the universe for a period of 25 years. Eventually, he comes back to Earth, and what happens? The traveler is now 10 years younger than the person who stayed behind on Earth. Does that make sense? I mean, we tend to think that time moves along at a methodical rate and both twins will age at the same rate. But yet this time dilation says that because this guy moved at high speeds throughout the universe, he is now 10 years younger. Let's take a look at another example. Now, scientists, that was kind of a mind game that Einstein played to try to explain this principle of time dilation. But we can go to actual experimental evidence. One form of experiment out there deals with clocks. You have two clocks. One clock stands still. The other clock is going to move. It's going to move relative to this clock that's standing still. Time dilation says that this moving clock is going to run slower. Is this true? Yes, it is. We have verifiable proof that a moving clock does indeed run slower. We have GPS satellites in orbit around the Earth. And the engineers had to put calculations into those satellites to deal with time dilation, so that when they communicate with a clock down on the Earth, remember the GPS satellite is moving at a relative great speed in reference to this clock on Earth, that's going to cause time dilation. They have to put in calculations to compensate for this time dilation. So clocks absolutely follow this time dilation. But clocks are a man-made technology. They are a technology that follows those two assumptions that Einstein made, the theory, principle of relativity and the invariant speed of light. The question is, does time dilation exist in nature? Well, physicists will point out other experiments. Probably the most famous one occurred at the top of Mount Washington in New Hampshire. Scientists at the top of the mountain measured gamma rays coming down from the upper atmosphere. They counted how many gamma rays there were there. They knew the decay rate of gamma rays. So they also went down to the surface and measured the amount of gamma rays making its way all the way down to the surface. They were expecting a low number down at the surface. But instead, they discovered that there was a much higher rate of gamma rays that were making their way all the way to the surface. Their conclusion is that this is being caused by time dilation. Now, keep in mind the air between the top of the mountain and sea level is not in time dilation. But these gamma rays going through the air are in time dilation. So we sort of got a situation here where same space, something is in time dilation, something else in that same space is not in time dilation. Does this make sense? I say no. And in one of my books on the Romeo Effect, there's having a series of books on the Romeo Effect, we will actually prove why I think that's wrong. That we do not have time dilation in nature. Alright, so time dilation is a situation where we kind of scratch our heads a little bit. To the physicist, time dilation absolutely exists. To the layperson, we're going, well, time is like the most steadiest thing we know of out there. You know, you look at the seconds of a clock, it goes around at a steady time. Without a steady time, we can't do certain fundamental calculations from physics, Newton's laws of motion. We have to have a steady movement of time. But yet, there's this time dilation that comes from Einstein's assumptions. So how can that be? So what we're going to do is we're going to develop a theory of time that is, as I said, a counter theory to Einstein's theory of relativity. What we're going to do in the theory of time is look at his assumptions and decide whether or not we think they're true or whether or not we think some modification is needed. Now, there's only three assumptions. There's the principle of relativity, the principle of invariant light speed, and this four-dimensional space-time. We will accept the principle of relativity. So, the principle of relativity as it exists in Einstein's theory of relativity is going to be exactly the same principle of relativity as I have in my theory of time. However, we're going to change his principle of invariant light speed. We're going to change it to the principle of non-constant light speed. So what does this mean? What is non-constant light speed? If you remember, when we were talking about Einstein's principle of invariant light speed, we said hidden in there was this idea that the speed of light was independent of its source. Okay? We're going to say that the speed of light is dependent on its source. What does this mean? Let's go back to the star that's going 1,000 miles per hour. When the photon leaves that star, under Einstein's assumption, that photon immediately starts going at speed c. Under the theory of time, on the non-constant speed of time, that photon will be traveling at c plus the 1,000 miles per hour that the star is going. For the case where the star is going 1,000,000 miles per hour, when a photon leaves the surface of that star, it's going to be going c plus 1,000,000 miles per hour. This is what we mean by the non-constant speed of light. In one case it was c plus 1,000. In another case it's c plus 1,000,000. And it's all because we are assuming that the speed of the photon is going to be dependent on its source. So that's part of what we're going to assume with the non-constant speed of light. There's another part. Einstein was not entirely consistent with himself at times. And so we're going to use another one of Einstein's ideas to kind of work against him. This other idea is Einstein's famous equation, E equals mc squared. This is the energy mass equivalence equation. And what it says is that if you have a photon, and that photon has a certain amount of energy, that energy corresponds to a certain amount of mass, or is equivalent to a certain amount of mass. So what happens is that when you have mass out there, you have got gravity affecting the mass. Okay? Now Einstein recognized that gravity seems to affect the photon. Part of his theory is that if you've got a massive object sitting out there and beams of light are going around this massive object, that the gravity from this massive object will bend the light rays. This was part of Einstein's theory. And it was actually proven. They looked at an eclipse of the sun, and they could see that a star that should still be behind the sun, they could see it because its light rays got bent by the gravity of the sun. Okay, so photons respond to gravity, but evidently only in terms of bending their path. According to Einstein, photons do not speed up or slow down as a result of gravity. Now we know here on Earth that when something falls to the Earth, it's going to accelerate due to the gravity of Earth. But according to Einstein, photons coming down do not change their speed. They stay going at speed c. We're going to argue that they actually do accelerate. That photons, as they journey through the universe, are affected by gravity, and they will accelerate and decelerate as a result of gravity. So, the speed of non-constant light is going to be based on two things. One is this dependence on the speed of the source, and the other is the gravity that the photon encounters as it's going through space. That is our non-constant speed of light assumption. Einstein's third assumption was this concept of four-dimensional space-time. In the theory of time, we're going to make that a five-dimensional space-time. Where does this fifth dimension come from? It's easy to understand back in Einstein's day why he would say it was four-dimensional space. Everything we look at in the universe is three-dimensional. And we know that time exists. Things move around in time. So it was obvious to Einstein and all the scientists of the time that we lived in four-dimensional space. Well, we now have satellites up in space that are taking observations of the universe. And something that's coming out of those observations seems to indicate that there is a fifth spatial dimension out there. We're going to call it the spatial time dimension. So, where is this spatial time dimension? It's in something called the multiverse. Now, we have our universe. And astronomers think that there is a bigger space that contains not only our universe, but many other universes. This space is called the multiverse. And when we look at things with these satellites, it appears that our universe is moving along another spatial dimension within the multiverse. So we're going to change Einstein's four-dimensional space-time concept to a five-dimensional space-time context. All right. In summary, in these lectures, we're dealing with the theory of time. The theory of time is a counter-theory to Einstein's theory of relativity. Our argument is that Einstein's theory of relativity is subject to the Romeo effect. The Romeo effect means that there are some bad conclusions being drawn because there are bad assumptions. Einstein made three assumptions, and we're going to claim that two of them are wrong. So what we're going to do in the next lecture is we're going to discuss relativity, the principle of relativity. We'll talk about those inertial frames of references. We'll also talk about accelerated frames of reference. We will also get into something called the Doppler effect. In the third lecture, we're going to attack this speed of light issue. Einstein assumed that it was an invariant speed of light. We're going to argue that the assumption really is a non-constant speed of light. And we will make that argument in the third lecture. In the fourth lecture, we're going to get into this concept of the new spatial time dimension. What is it those satellites are telling us that makes us think that there is another spatial dimension out there? So this promises to be kind of an interesting discussion because we're challenging the fundamental beliefs of our scientific community by coming up with a counter theory to Einstein's theory of relativity. I thank you for your time. I look forward to talking with you in our next lecture.